yeah, thanks, Steve, and everyone for having me and for tuning into this session. That was a really good introduction to kind of like this broader space of deep declarative networks and differentiable optimization and implicit differentiation. And I guess in this talk, I'm going to go deeper into a few more of the general principles behind the ideas in this space. And then towards the end, I'll talk about some of the newer work that I've been doing, mostly in the control space. So the rough division of this talk is that I'm going to try to spend about 15 minutes on this first part of differentiable convex optimization, which I guess in the framing of deep declarative networks is like one specific way of instantiating a deep declarative network that has a convex objective and maybe convex constraints. And then in the second 15 minutes, I'll talk about applications of doing this in the controls context, where you can think about your controller as solving an optimization problem, and you can use that as a node in your computation graph. And I guess getting back to some of the motivation that Steve said is what do we actually want to do when we're modeling in machine learning or vision or controls or other contexts? And I think modeling is still a really large open question of what the best way of modeling for certain problems are, or for when you have some kind of data or when you have a lot of data. And I think one huge question that a lot of people are asking is it okay if we can just throw a big neural network at this data and just kind of hope that it learns the right thing? So I'm talking about the standard kind of set of like linear algebra that you can throw at all of these vision and RL and language problems. And this paradigm seems to work really, really good when we have a lot of data and when kind of like the setup kind of matches the kind of like the magic that like deep learning has. And so maybe in settings where we have a lot of data and where we know the right pieces of modeling tools to throw at it, and we don't necessarily care about interpretability or some kind of really out of distribution generalization, then maybe it's okay to just throw a big neural network at your problems. But I think that there are still a lot of cases where you have some kind of domain knowledge and you want to open up your model a little bit more than the traditional models give you, where you want to learn certain parts of something that's more structured. And this additional structure, this additional domain knowledge can come in a lot of forms. It doesn't necessarily have to come in the form of an optimization problem like what I'm going to be talking about. But I will mostly talk about the optimization kind of like way of opening up your model and having specialized optimization components. And I guess as Steve prefaced here, is when I'm talking about optimization-based modeling in this context, I'm not talking about doing parameter optimization with some new optimization methods, or I'm not talking about gaining any new insights into optimizing the parameters of your model. I'm talking about having some kind of internal module or internal function where you can solve a sophisticated optimization problem that can represent a large class of operations, where you can kind of start opening up the what's like the computations in this optimization problem to help understand what's being learned, or to add some kind of structure or domain knowledge to what you're learning. And I think that optimization is a really great way of adding structure to problems, because it very naturally captures a lot of reasoning problems that we might have about the tasks that we care about. So for example, outside of the learning or vision settings where this space is a bit nicer, like if you have a really good analytic view of the problem that you're trying to solve, for example, a lot of problems in computer science can be, or controls or other fields can be formulated as just an optimization problem with no learning. It's it captures this essence of reasoning in a really powerful way. And it starts breaking down when you're in fields like vision, or when you're in like language or other machine learning settings where you have one piece of data or one type or modality of data that you don't understand. And that makes it really difficult to put traditional optimization methods on top of that to do this kind of reasoning, because you can't really analytically describe the properties of your data. So the kind of push for optimization-based modeling is based around this idea that you have some structure that you think you might want to have in your problem, and you want to learn parts of that you don't know, like for example, the parts that are coming from vision or some other high-dimensional space. But you want to keep this kind of reasoning component internal on top of the learning that you're doing. And I'll quickly talk about some of the applications of this, or the more concrete applications of this in RL control, game theory, and beyond. But before I do that, I'm going to talk a bit more about some of the foundations and kind of just like other bits of intuition to kind of make the fundamentals here a bit stronger. So one kind of way of thinking about how you can learn hard constraints in your model is you can imagine your optimization problem has this knowledge of some constraint set or some kind of parameterized constraint set. And this piece could be over some latent part of your data. Like maybe you know that your data has some kind of latent hard constraints. Like maybe it's some kind of language or some kind of a visual task or some kind of properties of the world make you think that there is like some polytope or something that's underlying your data. And what's kind of nice about optimization layers is that you can directly parameterize this constraint set and you can learn it from data, which is what I'm showing in this example. So the blue polytopes and ellipsoids are the pieces that are the true polytopes that's perhaps underlying some data process. And the red polytopes and ellipsoids are showing what happens when you try to learn polytopes to match the data. So that's just one kind of intuitive example of how you can use optimization layers. A few other interesting ones is that you can also interpret some of the standard operations that we're already using as themselves solving optimization problems, or themselves solving convex and constrained optimization problems. And this is not necessarily a useful tool to improve our understanding of like the ReLU, Sigmoid, or Softmax, but I think it's a useful tool for understanding how convex optimization layers can help with modeling, because it captures this rich class of say, in this case, activation functions. And it kind of gives you a feel for how you could maybe extend beyond these cases. So just to quickly go over these, so the ReLU you can interpret as solving this optimization problem that I have at the bottom, where you are let me just change this color. Where you at each point, say X is the input. At each point, you want to solve this quadratic objective, which I'm showing in the heat map here. And so say you have some X value of this point. You solve this quadratic objective, and you get out the identity function if you're in the positive part of the space, which matches the ReLU in the positive part of the space. And then once you start going negative, you just kind of chop the solution to the non-negative orthants, and that gives you the flat part of the ReLU. So that's kind of how you can translate what the ReLU is doing into this differentiable optimization view. And one thing to keep in mind, or one thing that kind of comes up in the machine learning setting, is that we really care about computing derivatives through these operations. So for example, the derivative of y star with respect to x. And this is really obvious how to do it in the normal ReLU case, because it's just an explicit closed form operation. But in the optimization case, it's not clear a priori that you could get any reasonable derivative flow through the output of this argument operation into the components of the objective or the constraints. In the ReLU case, it happens to work out. But there's not always a closed form solution to your optimization problem. Just to quickly go through these next two examples too, you can also look at the sigmoid as solving an optimization problem where it's kind of the same idea where you are projecting onto this, the 0, 1 box in this case, where if you kind of plot out this heat map or plot out this, the objective, you can get a sense of how this works. So at each point you solve this optimization problem, and turns out this entropy penalized objective gives you the sigmoid. And you can check that from essentially just differentiating this objective. The constraints aren't as important because you already have the entropy constraint here. And lastly, you can also do the same thing for the Softmax, where the Softmax is also just doing an entropy penalized projection onto the simplex. And you can also see this from taking the first order optimality of this optimization problem. And again, you have a closed form solution to this problem. And so the natural, I guess, generalization of these ideas is how do you handle arbitrary convex optimization problems that look like this, where you might not necessarily have an explicit closed form solution, and you're possibly also learning or parameterizing other parts of this optimization problem. So in these last few activation functions I showed, you typically just have this the inputs parameterized as the you're differentiating with just with respect to the inputs, but you can also parameterize these layers and learn other parts that perhaps stay fixed, kind of like the polytopes I was showing earlier. And I guess the one trick to differentiating through these optimization problems is that you just you can use the implicit function theorem in a lot of cases. And the implicit function theorem says, okay, we have a function f, which is defined as the roots of this g function. And we might not have a closed form solution to what f is, but we know what g is. And the implicit function theorem gives a way of computing the derivatives through f with respect to x in this way. And if you, I won't talk about this in too much detail, but if you think about what this is doing, is you can kind of imagine that it just has a good way of combining the derivatives of this g function along both directions that you kind of have access to. And this works under very mild assumptions. In most of the convex optimization cases, this is it almost always works. So I guess taking this piece, we can now take this and apply it to these optimization problems, or these more general optimization problems, to get the derivatives that we want for say like the machine learning setting. So if we start with a quadratic program, we have something like this. So we're filling in now the objective with maybe some parameters that are kind of shaping the cost and also shaping the constraints of the objective. So or of the optimization problem. And the only thing you need to do to get to this point to differentiating is you need to convert it into an unconstrained root finding problem. And in this quadratic program case, we can do this through the KKT conditions directly, where you have essentially this this mapping, or this kind of residual of the optimization problem, where you know that if you have some optimal primordial point Z, then if you're at the 0 point, then you know you have a solution to the original optimization problem. And so now this is an implicit function, and we can just apply the implicit function theorem to differentiate through this with respect to the parameters that we care about, which instantiating it looks like this. And now generalizing beyond this class of quadratic programs, because not every problem is a quadratic problem, and it's definitely worth thinking about how to differentiate through more complex optimization procedures. I guess long term, even non-convex optimization procedures or certain other more general classes. The only generalization I'll show in this talk is on conic programs, which kind of subsume a lot of convex optimization problems. So conic programs have this nice property where you can actually transform almost any convex optimization problem into the conic form that I have on the screen, where I'm writing it where this, in this case, it has a linear objective. You'd also imagine having quadratic objectives or more general forms here, and you have this constraint where this this mapping lies within some convex cone, where the convex cones can be some simple cones, like maybe it's just like this mapping is just zero, or you could have like the free cone or these other more complex cones like this second order cone, like this one, or a semi-definite or exponential cones, and you can take Cartesian products of cones. So these are really powerful representations of convex optimization problems, and the nice tools that we have for convex optimization, like CVXPy and this family of kind of languages that can transform optimization problems, it provides a really nice way of automatically transforming optimization problems into this conic form. And so now, if you want to differentiate through the conic form, you essentially apply the same trick where you just need to convert the conic optimization problem into some set of optimality conditions, which in this case comes from a slight change on top of the KKT system because of the conic constraints. But once you have that, then you also just apply the implicit function theorem and can easily get the derivatives that you want to have. And so now that we have this kind of like a toolbox or class of methods for differentiating through these class of convex optimization problems, we can think a bit more about applications. And there's definitely a lot of things that we could talk about here. I've left most of these applications out of this talk. So beyond like the hard constraints and projections that I mentioned earlier, I think there are a lot of interesting applications in game theory, or perhaps some kinds of economics, like either where you're finding equilibrium points or of games or of markets. In the control setting, which I'll talk about later, this can induce differentiable policy and control-based classes. In the meta-learning setting, there's quite a bit more to talk about than I have listed here. But differentiable SVMs are an interesting piece of meta-learning that you can do, where you can imagine just formulating the SVM like hyperplane fitting problem as solving a convex optimization problem. And also in the energy-based learning and structure prediction setting, if you have a convex inference procedure, you could, and that's something you can especially imagine differentiating through it. Even in non-convex inference procedures, you can also imagine differentiating through that in some other way. So I'll leave most of these applications out of this talk, but I'll focus on, I guess, one kind of more foundational one, and then I'll go deeper into this control part later in the talk. So I think one interesting generalization of this idea that you can project onto the simplex, and you can interpret the solution to that as the softmax. I think there's an interesting connection here to say vision and to other cases where you want to differentiate through the top K operation. And the way you can see this is that if you write out the optimization form for what the softmax is doing, is you can see that you can kind of interpret this constraint as saying find like the maximum, or find the almost maximum, like the vertices of the simplex are the like the maximum indices of whatever you feed into this. And you can imagine generalizing this so that you have this polytope that now has k active elements at each of the vertices, rather than just having a single active element. And we can kind of visualize this to get a sense of what this looks like. So just quickly going through these. So this is showing the penalty service actually on top of these polytopes, which comes in this case from the entropy terms. So the sigmoid, it's this box, and the vertices of the box are every possible combination of the like multiple labels you can have active. The softmax is just the simplex, where the indexes are just every possible active index you could have. And now as you extend to the top K setting, so for example, this is the top 2 setting. If you have 3 input items, it's every combination of 2 elements that you can have from your set of inputs. And you can start visualizing this in higher dimensions as well, like I have here on this hypercube. So if you have k equals 1, then you just get back the simplex. And then if k is 2, then you get back this other polytope that actually is also the simplex in this case. And as you go beyond to higher dimensions, you start getting these kind of more sophisticated polytopes where this is where you have 4 elements on the inputs, and you want to look at the space of 2 active elements. So that's the idea, that if you want to differentiate through the top K operation, you can just formulate it as this optimization problem and differentiate through this optimization problem. And I'll show an application of this in the control setting later in this talk. One last fundamental or foundational piece that I want to talk about is more on the implementation side of these methods. And it's that these methods do need to be carefully implemented. I want to talk about all of the details on the difficulties that come up here just for the sake of time, but it's quite challenging actually to efficiently implement these optimization layers. And I think at least in the class of constrained convex optimization problems, we're at a good point where practitioners can kind of just throw away all of the details about this implicit differentiation stuff. And in this case, we can just use CVXPy or some other kind of domain-specific language for prototyping these new layers, where it gives you a nice way of writing a few lines of code to construct and instantiate these optimization problems. And it has the efficiency of the past implementations that we've had that handle nicely the batches of optimization problems and so forth. And internally, this is just going through the differentiable conic optimization problem I mentioned earlier with another few pieces. Definitely let me know if there are any questions on this part, since I've gone through kind of fast, so that we can get on to this next part of the talk on differentiable control and reinforcement learning, which it looks like I have 5 minutes left. So I'll just briefly talk about some of the motivations in this space. So I think one longstanding question in the RL community and in the controls community is how we should formulate our policies, and if we can just throw a lot of data or simulations at black box policies that just directly map from some states to some action that we take. And I think it makes a lot of sense if we have a lot of data and we can allow a lot of interactions allow for a lot of interactions with the environment, then a model for reinforcement learning works pretty well. But I think in other settings, we do care about having some kind of more structure or knowledge about what's actually going on, about how policies are making decisions and how they're generating or potentially using future plans. And I think control is a good way of adding a structure, which is used in a lot of cases where you perhaps know the costs that you want to optimize on your system, and you know how your system works. You can just formulate it completely as an optimization problem without learning. And then maybe when you start moving to higher dimensional systems and you don't know how your system transitions, or you don't know the cost that you want to optimize, especially in visual-based robotics, where your robot takes in vision as a state space, it's quite difficult to write out the cost of the controller that you would want to optimize that perhaps is beyond some of the goal-driven or goal-oriented cost functions. So one issue, it's a more fundamental problem in this space when you're learning parts of your control problem, or when you're learning components that are going to be put into the a controller is something I'm calling the, or we're calling the objective mismatch problem. And this problem comes from having a policy that's interacting with the environment and receiving responses from that environment. And the responses come in the form of state transitions and also rewards. And what people typically do, it's not always like this, but typically you would, if you don't know the dynamics of your system, for example, you would fit those with maximum likelihoods to your observed state transitions, and you would then feed that back into your controller that induces some other policy. And what I'm calling the mismatch problem is, I think, really crucial and really a really hard challenge in the field is that if you fit your dynamics for maximum likelihood, it doesn't necessarily understand this like reward, or it doesn't have any signal of the reward that it's actually inducing. And so you can run into these weird situations where maybe your environment has a lot of really irrelevant parts to it, but because you're failing the maximum likelihood, then you're trying to put a lot of modeling capacity to these parts of the environment that don't matter at all for the reward that the policy is obtaining. And in fact, these complex parts of the environment can distract significantly from the reward. So I think there are quite a few solutions or proposed ways of mitigating this issue, where I think differentiating through a controller is one way of thinking about kind of getting around this issue, because it allows you to directly inject knowledge of the reward signal into the learning of say, your system dynamics. So this kind of gives you this a replacement for black box policies in some settings. And you can just kind of plug it in anywhere you can plug in a black box policy. And skipping over most of the details for now, is that there are actually quite a few ways of instantiating differentiable controllers. This is one that we were doing a few years ago, is on differentiating through a chain of quadratic programs, where this is the state of the art for a lot of optimization or a lot of controls problems where you kind of know that you have a low dimensional space. I'll skip over this slide. There's interesting connections to differentiating through LQR. And a second idea in this space is that you can also differentiate through these optimizers that generate sequences of samples rather than, I guess, like the other kinds of like unrolled optimizers. So instead of unrolling through gradient descent, you can unroll through optimizers like the Cross-Entropy method that generate sequences of samples. And this is also nice because the Cross-Entropy method is also a state-of-the-art controller for model-based RL. It looks like I'm at the time limit, so I'll just spend a few more, one more minute just closing off. I don't have that many more slides. So yes, the differentiating through the Cross-Entropy method is actually easy if you just use the top K operation. And you can start applying it to these kind of more non-trivial systems where you can start fine-tuning and trying to fix the objective mismatch issue and some of these settings where you're generating these very long horizon predictions of your dynamics, like this cheetah. There's another interesting idea that's in the paper of how you can use this to exploit the solution space structure, which is kind of orthogonal to this objective mismatch issue. But I will defer this to any future conversations we may have. So with that, that's all I had to talk about today. And yes, thank you for coming. Thank you for having me, to the organizers. And yeah, I look forward to the rest of the workshop.